Have you ever watched a stock form a technical pattern and wondered how many times does that pattern actually work out? What is the win rate? Well, my name is Ben, and today I'm presenting Chart Mapper, which I call the reverse image search for stock patterns. This presentation is going to have an explanation followed by results. Then I'm going to talk about flaws and future improvements that I can have. And then at the end, there's going to be a code demonstration. So if you're just here for the code demonstration, go ahead and skip the last 2 minutes of the video. So let me draw your attention to this chart. This shows what I call a stock pattern or a setup. And it all started off with a simple question. What if you could identify every single time that exact stock pattern has occurred within the last year? What would that mean to you? Well, for me, it means I have much more reliable backtesting statistics. So for example, let's say the last 4 times that I've taken this trade, I've won 100% of the time, and my risk reward is 3 to 1. So in theory, it's an amazing trade. I should take it every time. But what if in reality, it has a win rate of just 1%? 99% of the time, I lose. And the 4 times that I won was just luck. Would that be terrible? And that's what Chart Mapper aims to take away. It'll give you a much broader and more reliable backtesting statistics. In addition, it'll also allow you to identify variables that actually matter. So for example, if you have an engine that is supposed to predict if this athlete is going to make it to the NBA. So for your test data, you have 3 athletes in the NBA and you have 2 variables. So the first variable is vertical jump, and the second variable is does he have a wife? So these 3 athletes, they have a vertical jump of 37, 40, 42, but they all have in common is that they don't have a wife. Now you get your test subject. This athlete has a vertical jump of 46 inches, but he has a wife. Does that mean there's no way he's in the NBA? No. This variable of having a wife or not does not matter in regards to the output. It doesn't matter at all. And that's what Chart Mapper aims to eliminate. It tries to find what variables actually impact and affect the trade setup. So what is Chart Mapper? It's a program designed to search for technical patterns within a larger data set. But how? Can you just give a program an image or a picture of a stock chart and it'll just output exactly what you're looking for? Well, I guess you can, but it'll be very computationally expensive. You'd have to implement machine learning. You have to teach the program visually how to identify stock patterns and how to identify the difference between stock patterns. And that's very hard to do. So I took a different approach. Instead, what if you could assign a numerical value to every single candle, if you're familiar with candlestick charts, a numerical value to every single candle within the stock chart. So whenever you're looking for a certain pattern, all you need to do is just run a simple numerical search. So for example, if you're trying to look for 3 candles and the first candle went up by 10 points, so it has a value of 10. And then the next has a value of 5, next has a value of -5. So if you want to look for this pattern within the larger data set, all you need to do is search for, okay, how many times has 10, the sequence 10, 5, and -5 occur within the larger data set. It's so much easier, so much more approachable, and much less computationally expensive to implement. So let me walk through the steps that Chart Mapper takes to execute this. So first, you need to get the data. So I wrote a thing script which allows me to export tick data, candlestick data from Thinkorswim, and then once you have the data, you need to format it. So then that's where data normalization comes in, and I use log scaling and min-max scaling. So in this picture right here, it shows you why we use log scaling. First of all, obviously you can't use numerical change. For example, if you had a stock that is worth $2 and it increases by $1, that's a 50% change. But if you have a stock that is worth $1,000 and it increases by $1, it's nowhere near the same magnitude as a $2 stock. Although they both increase by $1, yeah, but the magnitude is much more different on that $2 stock. So you can't just use numerical change. And then percentage change. Well, percentage change is just used to compare 2 points in time. It's something you would use to compare what is the change from 2020 to 2019. But candlestick charts are continuous. They happen one after another. As soon as one closes, another one opens. And sometimes they even happen within the same minute. So with these continuous types of graphs, it's very hard to use percentage change because of how it's computed. So right here, the formula for percentage change is new minus old divided by old. So if you have a candle that started at 100, it goes to 120, and then the next candle opens at 120 and goes to 140, let's calculate the percentage change of that. So from 100 to 120, it's 120 minus 100 divided by 100. So that's around 20%. But then the next one, it goes from 140 minus 120, but now you divide it by your old, which is 120. So instead of 20 divided by 100, now you're dividing 20 by 120. So instead of your percentage change of 20%, now you have a percentage change of 16.66%, which is different, drastically different compared, even though they both increase by 20, the percentage change is much different, and that's just one candle apart. So the reason is because the denominator is changing. So what log scaling does, it just eliminates the denominator entirely. So right here, if you do natural log of 120 minus 100, you'll get around 18.33%. And if you do the same thing from 140 minus 120, the natural log of that, you'll still get 18.33%. So now it just normalizes all of the percentage change on the equal playing field. And this effect really shows itself in times of increased volatility, because when prices change so quickly, then the denominator, if you're using percentage change, it'll just completely mess up and it'll just skew your chart and it just look really bad. So that's why we use log scaling. And then once you assigned your candle values, now you have to find the patterns, and that's what we use for sequence matching. So there's different algorithms that we can use to match the target with the larger data set. So what I used was the Levenshtein distance and the absolute numerical difference, which I'll explain later. And then the final step, once we found the target within the larger data set, we just need to visualize this sequence within a chart. So that's what we use. We visualize it with Plotly. Let's go more into sequence matching. So the Levenshtein distance is called the edit distance because it calculates what is the minimum edits you can take through either insertion, deletion, or replacement to match the two numbers. So it treats it as a string. So let's say you have 100 and your target is 80. So it treats it as a string, and what is the minimum amount of change that you can make to 100 to change it to 80? So first, you replace the 1 with an 8 through replacement, and then you delete the 0. So it'll have edit distance of 2 because there's 2 edits made in order to change 100 to 80. And what I've noticed with it is that it gets more accurate with larger sequences, but it might get too accurate with no diversity. And when I visualize this, you'll see exactly what I mean. But what I do like about it is that it's a rolling search. What that means is that, so let's just say you have a larger data set of numbers from 1 to 10, and you're trying to find is 5, 6, 7, the sequence 5, 6, 7 in 1 to 10. Well, you can't just search by threes. You can't search, okay, 1, 2, 3. Is that equal to 5, 6, 7? No. And then 4, 5, 6. Is that equal to 5, 6, 7? No. And then if you keep on doing that, if you search by threes, you're not going to find 5, 6, 7. But we do know that when you're counting from 1 to 10, obviously 5, 6, 7 is between that. So instead, you need to do a rolling search, which instead of taking it by threes, it increments it by 1 every single time using matrices. So say, okay, it's 1, 2, 3 in 5, 6, 7. No, it's not. So now it shifts it over by 1. So it's 2, 3, 4 equal to 5, 6, 7. And then it shifts it until it finds 5, 6, 7. And that just makes the search much more reliable, as it doesn't just cut in between the sequences. And then the other one is absolute numerical difference, which is simply just the absolute difference. So going back to the example with 180, if you have 100 and you're trying to get to 80, instead of treating it as a string, it treats it as a number. So it just takes 100 minus 80 and then the absolute value of that, so which is 20. So the difference between is that Levenshtein you would have gotten 2, this one you would have gotten 20. And what I've noticed with that is that it's much less variance with smaller sequence, but the larger you get, the more numbers you add to the sequence, the more variance you'll get. And that's just because it treats it as numbers. So with more numbers, there's a higher range that you can have. And it's also a rolling search. So let's see it in action. So here are the results from the Levenshtein distance. So as you can see here, with a smaller sequence like this search only has like a few, like 8 candlesticks, while this one has like much more. So with the smaller sequence, you see the most similar and the second most similar, they look pretty much the same, relatively. But then when you compare to the third most similar and the fourth most similar, they don't look the same at all. They look nothing like the first two. But when you go to a much larger sequence, these are the top 4, and they look like almost identical. And well, that because they are identical, and I'll explain that later when we demonstrate the code. And absolute distance is actually, I got opposite results. So with the smaller sequence, you see these top 4 charts are relatively similar, but with the bigger sequence, the top 1 and top 2, they are pretty similar, but then number 3 and number 4, they don't look anything alike to the rest. So yeah. So now the flaws. 2000 tick data. So right now, Thinkorswim doesn't have like super precise time measurements. So it only has precise up to the exact minute. But for ticks, sometimes ticks form so fast that they form multiple within the same minute. So if you want to include time into your calculations, you need to have a data source that can track it down to the exact second. And right now, we don't have that. So that's why it's not even included in the chart. And you'll see that once you see the chart. Second is data normalization method. So I'm using log scaling and min-max scaling right now, but in the future, there's like standard deviation that I can implement, which I don't know how it'll impact, but it'll definitely make the code much more efficient. And then number 3 is matching methods. So as you saw before with the Levenshtein and the absolute difference, there's the pros and cons to different types of searches. Um, and the more searches you have, I guess it's just a trial and error and see which one works most for your use. So I know like in the future I can implement like the rapid cart algorithm, which implements like a rolling hash search. So I don't know how effective it'll be, but it's just more trial and error to see what truly works because there are still flaws within the Levenshtein and the absolute numerical difference. Um, it is computationally expensive, especially the Levenshtein. The bigger your data set gets, the more slower it takes to output the code. And number five is user interactivity and visualization. And that's like one of the most immediate improvements that I am to make in the future. So let's just go to that. So right now I have to literally input the target sequence within the code and then run the search within the code. But in the future, I hope to implement like a user interface where wouldn't it be nice if you could just like select a group of candles and it'll just output similar setups to you instead of having to type every single individual candle value into the code itself. It'll be much easier and much faster in the testing process. I'm experimenting with Python Qt5 or Tkinter, and maybe even C++ if I need something more advanced. And also, there's more methods of sequence matching. So as we stated before, like there's pros and cons with Levenshtein and absolute numerical difference. So just trying out more algorithms that can match the candle values with the overall data set just to figure out what truly is the best. And that's it. So now let's get into the code. So this is Visual Studio Code. So it all starts off with the input data. So this data was taken or is exported through my Think script from Thinkorswim, and I converted it to an Excel sheet. So the Excel sheet has open, high, low, close, just the standard data from a candlestick chart. And then once you have your data, you need to assign the candle values to that data. So that's what this code does. And when I run it, the output, it's outputted here. And it keeps the same, but it adds a column, which is candle value, which is calculated based off the log percentage change as we discussed earlier. And there's also like a data sheet, which gives you like the certain stats and the range. It just helps me know that my code is working. And so once you've assigned a value to every single candle, now you're able to run a search. So there's a different search methods, so like the Levenshtein search and the numerical search. So you can do both. This code right here, it searches for, so here's a target sequence. This is what I was talking about earlier, where you have to input directly exactly what you're looking for inside the code itself, and then it'll run a search based off of that. So once you have a target sequence, you run a search, then it'll output on an Excel sheet. This is all the matches. So it's from ascending order. So what is the most closest, and it gives you like the indexes, so all the locations for the candles. So once you have all of the candle locations, now all you need to do is just find where it is inside the graph and then just plot it out. And that's what this code does. So when we run it, takes a while. It outputs a graph, and so this is the number one most similar, and then number two, number three, number four, and etc. And then we can do the same thing for the Levenshtein search. Here. So once again, this is the most similar, and then number 2, number 3, number 4. Yeah. And then all of these charts are just stored in the HTML plots. Yeah, and that's about it. I might have left a few things out unintentionally, so if you have any questions, just let me know. This was a presentation on Chart Mapper. Hopefully, you have a better understanding. Thank you.